Hello everyone, I'm Wei. Let's get started today's lecture on convolutional neural network. In the last lecture, we have learned recurrent neural net, and today we will learn how to use convolutional neural networks to solve NLP problems such as test classification. Why we need convolutional net? The first reason is that with standard multilayer perceptrons, one always expects um, the input have the same length, but in NLP tasks, um, the sentences are always have the sentences always have different lengths. So we cannot just apply the multilayer perceptrons to solve NLP problems. The second point is in multilayer perceptrons, every neurons in the first layers are all connected to the every neurons in the following layers. But we know many words in the sentence are not very informative, so we don't want to connect these unnecessary words to the following layers. The last point is multilayer perceptrons always have too many parameters, so we cannot train such models uh, on some language to which we don't have much data available. Okay, today's lectures. In today's lectures, we will cover um, the standard techniques like convolution and pooling operations. Then we will cover some NLP applications which can be solved by convolutional neural networks. This lecture is based on two videos given by Stanford researchers. Let's see the general idea of the convolutions. You've Goldberg, who said uh, a convolutional neural network is designed to identify indicative local predictors in a large structure. Okay, what's the meaning of the indicative predictors? For example, um, a boy is very happy. We want to label this. We want to label this sentence with either positive or negative meanings. Okay, so we can find there's a keyword happy, right? And which are the very strong signals to the label predictions. And if we apply the convolutional neural networks, and we can easily identify uh, such keywords like happy as predictors. Okay, let's have a look at the convolutional operation, which is initially applied in images. For example, on the left side, we have an input image with binary values, and one need to extract the indicative predictors, which we call the convolved features, as we can see on the right side. And with convolutional operations, uh, one can do this feature extractions by using filters. For examples, we can apply the filter to the image um, and multiply every values in the image by the corresponding values in the filter. Then we sum them up. And in order to get the convolved features, okay, and we can execute these operations many times in order to get all the features in the convolved feature tables. Okay, but we know that the convolutional operations are not sensitive to the word order. for example, we have the sentence here, a boy is very happy, and each row vector is an imbalance, okay? And if we switch the order, if we reverse very and happy, and the convolved, we can see the value of convolved features is identical, right? So uh, would it be matters? Would it matters for the NLP applications? Okay, okay. For example, test classification, uh, and sentiment classification. Okay, so we have different sentences and where we have some keywords. And we know that these keywords can be extracted by the filter and which is able to generate indicative predictors. So these keywords are indicative predictors, and but obviously they are in the different positions. They're at the different positions of each sentence, right? Right. But the labels for these, all these sentences are labeled with positive, right? With positive meanings. So for such tasks, and position information does not really matters. So we can safely use convolutional operation and convolutional neural networks to solve the test classification problem. Okay. Let's have a look at the dimensionalities of image and text. Images usually have two dimensions, which are rendered as a matrix, but sometimes they have three dimensions if we consider the RGB channels. Okay, but in contrast, uh, text flows are usually have only one dimension. Okay, let's have a look at the 1D convolution operations. Suppose we have F as input representations, and we also have G as a convolutional filter, and now we need to compute the convolved features at position I. Okay, then we suppose position I is here, and we consider m equal to 2, then we can get the vectors for f, right? And we also can get the vector for g, which has the same size as f, right? And now we can obtain the convolved feature at position I, which is equal to the inner product of vector f and vector g. Okay, when it comes to the NLPs, and we can see here the fi minus m is not a scalar anymore. Instead, it's vectors with the dimensions, because for every word in the sentence, we always can find vectors as their word embeddings. And similarly, we can find the convolutional filter G as vectors with the same dimension as F. In this slides, we name them with different notations, and we make fi minus 1 as xi minus m, right? And we also name gm as wm, right? Okay, so we can see here we have the f here, right? And we have the f here. Now f is now we have f here, and which is a matrix, and if we consider the regions of the f, right? And now we also have the g as another matrix with the same size as f, right? And now we can get to the convolved features. We can get to the convolved features at position at a position I, and which is equal to the element wise vectors, which can be computed by the element-wise multiplications of F and G, matrix F and matrix G. Okay. Then we can follow this operations many times in order to get different convolved features at different positions I, right? Okay. Here's the short summary of the convolutions. And the first question is convolution for test in 1D or in 2D? If we consider each word in the test, in the sentence, is a vectors, right? And of course, the convolution operations is executed in 2 dimensions, and can also interpret input fi minus I minus m and g m are lying in the d-dimensional space. Yeah, this is obvious answer because if we consider the convolutions is worked on the 2 dimensions, of course fi minus 1 and gm would be vectors with d dimensions. Let's have a look at the properties of the convolutional networks. The first is sparse connectivities. As examples here, we only have the first 3 tokens are connected to the first neurons in the next layers. And as for fully connected layers, the every word in the previous layers are supposed to be connected to every neurons in the next layers. As the second, the properties of parameter sharing, and we can see here in the top layer we have 4 convolved features, right? Which are obtained by applying the convolutional filters, right? So we have 4 convolutional filters here, and the parameters in these convolutional filters are totally shared, which means one can largely reduce the amount of the parameters and such neural networks. So such neural networks can be trained on very little training data. Now let's have a look at the strit. Strit specifies the step sizes for for moving over the sentence. For example, if we consider strit as 1, and okay, let's see, there's 4 convolved features on the top layer, right? And which means we have the 4 convolved, which means we have 4 convolutional operations. Then let's have a look at the 2 convolutional operations here, and the starting position of these successive convolutional operations are shifted by 1. So if we consider the strip as 2, the start position of 2 convolutional operations are shifted by 2. Okay, and in theory, a convolution layers could handle sentences with different lengths, but in practice, we always consider the sentences with the same length, just like what we use in the multi-layer perceptrons. And we can do this by applying paddings with some zeros. This is empirically important because in this ways we can save a lot of, we can make very fast computations because TensorFlow and PyTorch because if the sentences have the same length, then we can make them as a matrix, and all the computations are based on matrix. and the TensorFlow and PyTorch based on GPU can largely benefit to such matrix computations. Okay, let's look at the pooling layers. The general idea is to capture the most important predictors. Suppose we have a number of convolved features from C1, C2, and so on. And if we are most interested or we think the master values of these convolved features are most important, then we can apply the max poolings. Okay, and likewise, if we think the mean value or the average values are important, then we can apply different pooling operations. Let's look at the convolutional networks in a whole. We start with a sequence of words as input and feed them into a lookup layers to get their word embeddings. In this example, every word embedding has two dimensions, and then we feed these word embeddings into convolutional layers. First, we start with four convolutional operations, and to get four convolved features, right? And we can apply the nonlinear activation functions and to amplify the signals of these convolved features. And in these examples, we are most interested in the max values of these features. So we apply the max poolings to get the value that are most prominent to this task. Then we feed these values into a softmax classifiers, but we are working on the binary test classification, so we can just apply the sigmoid functions, and in order to constrain the outputs into the interval from 0 to 1. And we can see in these examples, the models is most likely to label the sentence, the movie was awesome, with the positive meanings, right? Now let's discuss the property of the poolings. The idea is to extract relevant but prominent features independent of their positions, which causes two problems. First, the times of the predictors are neglected. For example, we can use convolution operations to get one time to get a great predictor, one time great predictor, and three times horrible predictors, right? But if we apply the pooling operation later, and we will only get one time great and one time horrible as predictors. So the prediction of this sentence become unclear. The second problem is word order is not considered. Obviously, the first sentence should be labeled negative, and the second sentence should be labeled with positive. But if we apply pooling operations, the order the order of love and hate cannot be recognized. So the models would likely predict these two sentences with the same label. Let's move to the next part, convolutional networks for NLP. And there are many NLP problems that can be solved by applying convolutional networks, such as sentence classification, semantic role labeling. And usually we combine convolutional networks with word embeddings. But there is another option that we can build convolutional networks based on character-based approach. This is because unlike many Indo-European language where words are considered as minimal unit, many other languages like Chinese and Japanese, there is no space between characters, which makes word segmentations very tricky. To solve these problems, some researchers propose a character-based approach coupling with convolutional networks. They consider the character as a minimal unit, which leads to a much smaller vocabulary. And this approach can be applied in many NLP tasks. And in the literature, we can find such approach can compete with the state of the art of a word-based approach, but it usually requires a large data set. So in practice, we prefer word embeddings instead of character-based approach. Okay. Let's look at the summary of this lecture. In this lecture, we have talked convolutional networks which can deal with the variable sized input, but in practice, we usually use paddings to make our sentences with the same length because we expect faster computations based on metrics. And we also learned two properties of the convolution networks, so-called sparse connectivity and parameter shares. And we also learned the pooling operations, and which can extract the most relevant and prominent predictors. And we also learned some NLP applications to which we can apply convolutional networks. Okay. That's all for today's lecture. See you next week. Hello, everyone. Let's move to the CNN exercise. As usual, we provide with the bingo question and the theoretical questions, and both of which are not difficult. I believe you can solve by yourself. And for the last questions, which is about computing the dimension and the parameters, so it needs some small calculations, and I will make a brief discussions on this question. Okay, let's look at an example. Suppose we have n words as the input, and we feed them into a lookup layer, and from which we can get word embeddings for every word, and each embedding has the dimension size, for example. To do this, we need a matrix W1 in lookup layer with the size of vocabulary size V times dimension D. Then we can, next we feed these word embeddings into the convolutional layer. First, we need to define the filter F. Suppose the F has the size of 2 times D, then we can extract a number of predictors, and namely we will have n minus 2 plus 1 predictors, and then we apply the pooling operations because we are most interested in the most relevant the predictors, most important predictors. Okay, but sometimes the only one prominent predictor is not enough, so we will use M filters. Then we can collect M predictors, right? We can get M prominent predictors. Okay, if we are working on the binary task classifications, and one expects a single neurons in the last layers and for the model prediction. So we need feed these. So we need to feed these predictors, M predictors, into a linear classifier, and to make some transformation. So we need another matrix in the linear classifier, W2 with the size of M times 1. So we can find here W2 and linear class and M predictors have the same size, so we can make the inner product of them to get the single neuron as the output, which is the model prediction for the task. Okay, I think that's all for today's exercise. Yep, see you next week.